Hello.
Yeah, you are audible, Saifa.
Good evening, everyone. Is it audible?
Yes. Your voice is clear.
Good evening, everyone. A warm welcome to all of you to session 3 of our AICTE sponsored faculty development program. Let's begin today's session with great enthusiasm and active participation. Our today's topic for session 1 is artificial intelligence in cardiac image reconstruction. And our eminent speaker is Dr. Archana V. Malagi. And let me introduce Archana V. Malagi. Dr. Archana V. Malagi is a postdoctoral researcher at Cedars-Sinai Medical Center, Los Angeles, specializing in biomedical engineering and computational biology. She earned her PhD from Indian Institute of Technology, Delhi, and is presently engaged in developing next generation cardiac MRI technologies to improve the diagnosis of cardiovascular disorders. Her research is focused on creating a non-invasive and comfortable imaging method to detect coronary microvascular dysfunction, CMD, in women, which is a condition frequently undetected by routine tests. By applying advanced MRI techniques, including phase resolved T2 star mapping, suspiciability imaging, she aims to facilitate early and reliable diagnosis of CMD. On behalf of KMEA Engineering College and all of us, I welcome you, ma'am, for this today's session.
Yeah, thank you very much for this great introduction. So, can I start the session?
Yeah, it's yours.
Okay, thank you. First of all, I would like to thank Dr. Rafiq sir to invite me for this lecture and session. So today we'll be covering regarding, as ma'am said, AI in cardiac MRI, it's magnetic resonance imaging, and reconstructing those images. So the outline for this presentation is that we'll be covering what is cardiac MRI basics and what is MRI, and then a little bit about deep learning fundamentals and different architectures used in cardiac MRI. Like for example, there are unrolled model-based networks, and then various imaging used in cardiac MRI, like for example, CNA imaging, and how there is different aspects of MRI which causes an issue, and how the AI is able to address those issue. For example, if there is any motion in the image, how it can correct. And different architecture. Also, we'll be talking about UNet. We'll be talking about transformers and emerging approaches. And at the end, we'll be talking about how we will be using this AI into the practical cardiac MRI for helping in the diagnosis of different diseases. And also, we'll be talking about the different model, open source model and open source data sets which will be available in the internet. And there are different challenges and future direction which we'll be talking in this presentation. So now let's talk about cardiac MRI. Cardiac MRI is a very powerful tool, and it's a non-invasive tool to see the detailed structure, functional, tissue-specific informations. But there are different challenges while doing cardiac MRI. Is that it's a long scan time. The patient needs to hold his or her breath during the scan, and it becomes very difficult for patients with older age. And also there are arrhythmias where the heart rate are not like for example, heart rate might increase or decrease drastically, and it becomes difficult to image certain cardiac phases like systolic in the sense heart contracting, relaxing. It becomes difficult to image those images, and the radiologist or the clinicians, it becomes difficult for them to see those images. So how this AI can help us in seeing this image reconstruction will be coming into this pictures. In what is AI image reconstruction is that what we are doing is we are taking a picture, and those pictures is very difficult to take in this computationally. So what we do is we convert those image into Fourier transform, and then we are able to see how an cardiac MRI looks like. So you can see the routine protocol. It's very long. So first, what we do is we image the video where we are able to see the contraction and relaxation in a different view. So this is the heart where we are able to see the four chamber, right? This is left ventricle, and you can see here left atrium and left ventricle, and this is right atrium and right ventricle. So you can see the wall is very thick around the left ventricle, and usually we image those part of the region where you can see the myocardium in a better way. So this is a myocardium which is surrounding the left ventricle, and this is the right ventricle. You can see that. And this is the two chamber. This is two chamber where you are able to see only left ventricle and right ventricle. So this is diastolic, means the heart muscles are contracted, and this is systolic. So sorry, this is relaxation, and this is contraction. So here you can see different modality that the technician needs to acquire. So this is the cine images, and then these are called T1, T2. These are different contrast from the MRI, which we are able to appreciate through the images. You can see this is called native T1, T2, and these are this black and white images. What you are seeing here is it's a phase contrast images where you are able to calculate the blood velocity using the images. And then what we do is we administer stress agents. So we want to know how the heart performs, the heart function during the stress. And then we calculate different cardiac output using this images. So this is the overall cardiac protocol which radiologists use. Now let us come into what is MRI. MRI is a magnetic resonance imaging. As you can see, this is the, as you can see here, this is the MRI setup, and what you see here is this is a outer layer. Outer layer is the supermagnetic uh, coil surrounding, and then inside there are gradient coils. So gradient coils are used to localize the pixel from, we need to know where the particular voxel signal is coming from. So we use the gradient coil, and also we use the radio frequency. The radio frequency coil, it's specific to different body region. For heart, we use, you can use a thoracic RF coil, which we keep it on the patient. And what we do is this RF coil is used to excite the proton inside our body, and it is then the signal coming from that proton is captured using this RF coil. And then we also use different set of gradient coil to image different areas of the body. One of the main advantage of MRI is it's a non an ionizing radiation. As you can see, we can image different part of the organs like brain, heart, liver, and joints as well. Now let's come into the principle. So our body consists of 75% of water. So what happens is the water consists of hydrogen proton. So they are aligned in a different directions. They are randomly oriented. Now what we do is, as soon as the patient enters into that inside the bore, so what happens is all the proton is aligned in one direction along the magnetic field. So what happens is that the total net magnetization, the proton is in one direction. So now if you want to image a particular region of the body, what we do is we send radio frequency. So you send a radio frequency in a certain angle, that is 90 degree. And what happens is this proton, which is aligned in one direction, it changes its direction to the RF. So it absorbs the energy of the radio frequency, and it changes its direction. So we keep the radio frequency for a certain period, and then we switch off the radio frequency, and those spin comes back to its position. While it is coming back to its position, it releases the signal. So this signal is captured by the radio frequency coil, and you can get a different variety of contrast. So if the the signal which is coming has low duration, then the intensity might be less. If it is high, the duration of that signal is high, then that intensity will be darker. Like for example, the darkest will have higher duration, then it becomes dark in the MRI images. This is an representative MRI imaging. So this is the principle of magnetic resonance imaging. So now this image, what you are seeing is how do we get that image? So the overall contrast is that before this image is generated, there is a key space. Key space is nothing but it's a raw data of that image, which is generated through MRI scanner. It is in the Fourier domain. To get that K space into image, we need to do inverse Fourier transform. Yeah, think about it as a musical note, and then reconstruction is a full melody. So you can see here that it's a case space. So this is an example of a case space, which we get through MRI scanner. This is a raw data, and each part of this is a pixel. And if you do inverse Fourier transform of that pixel, that is kx along this direction and ky around this direction, you can get an pixel voxel here. You can see here. This is an image corresponding to this. If we do inverse Fourier transform, we get this particular voxel intensity into imaging space. And if you want to get the K space again, then you need to do Fourier transform of this image, and then you get the K space. So how do we get this K space data? So you cannot just get the K space in one go. So what we do is there are different ways to acquire the K space. So what we do is we acquire one line of that image at a time, or we will use a train like trajectory, like zigzag kind of key space. You can see it's zigzag way to acquire those key space. And this spiral way is you are acquiring the center part and then going to the periphery part. One more thing is inside the K space is that most of the information higher frequency component, everything is present within the center of the case space. This center case space has all the information about the images, and as you go to the periphery, it contains more about information about the edges.
Archana,
So
one second.
yeah,
Sorry for interruption.
no problem.
Participants, please off your video, please. Okay, continue.
Yeah, no problem. So what happens is the center part has all the information about the images, and the periphery of the case space has information about the edge between different region, different voxel. So the center in spiral trajectory, what we do is we acquire the center part and then come to the periphery part of the case space, and then there is radial. So radial way is like from center, one line is acquired to the periphery. So these are different trajectory choices which you can use. This helps in like, for example, ecoplanar imaging, that is a zigzag way of acquiring case space, helps in getting that scan speed. You can acquire that image within a second, and then it's also resistant to motion. Some of the trajectory, for example, radial trajectory, if we acquire the case space in a radial trajectory, if there is any motion in the image, that can be corrected through radial corrector. And also one of the issue of some of the trajectory is reconstruction complexity. So now what we do is, now we have this case space. How do we reconstruct one at a time using this spiral? For example, spiral and radial becomes very complex to reconstruct because it's non-Cartesian, and the Cartesian is very easy. You know that this line belongs to that particular imaging line, but in spiral, it's a circular region. So you need to apply a complex mathematical uh, tool to reconstruct those spiral and radial trajectory to get that particular spatial information. So as I explained, the traditional way to construct an image is using Fourier transform, and where you convert the case space into imaging space. To do those reconstruction, there are various way. Like for example, we use parallel imaging, compressed sensing. These are the techniques used to fasten the reconstructions, but it has a limitation. Limitation is because these parallel imaging, compressed sensing are iterative in nature. So they are processing the imaging line one at a time through loop. So it takes so much time. So you need to have very high computation power to speeden up those reconstruction. So you just imagine that you're reading one line at a time, so it takes some time, right? So similarly in MRI scanner, it is reading one line of that image at a time. So these are different techniques, but it has limitation that it needs to undergo through loop. And also these kind of parallel imaging, what it does is it uses limited resources. So we see artifact in the images, so the quality of that image is very low. And also this kind of limitation motivate us to use AI based reconstruction. Now let's compare what is the amount of time a classical reconstruction and AI based reconstruction takes the time. So you see, this is the uh, traditional reconstruction. You can see it takes a lot of time, like 300 seconds to get one image. And there are different ways that you can use the AI. You can use the AI plus the compressed sensing. Compressed sensing is also one of the classical reconstruction method. And if you use it with AI, if you integrate the AI, then it reduces the time by half, that is 150 seconds to get an image. Now, if we use purely AI-based reconstruction, this is one of the reconstruction where we are using the motion and motion-based reconstruction. So you see there is like 10-20% decrease in the uh, time, scan time. So you have from, if you compare it with 300 to 100 seconds, so you have reduced drastically. So you can see uh, within like 100 seconds, you have one image with AI-based reconstruction. In terms of cardiac MRI, you can get the whole 3D based cardiac images within 2 minutes. So you see how AI can help us getting the image uh, faster. So what is the need of the AI model is that we have faster imaging. There are less artifact, high quality images. So this is an example flowchart. Like for example, you can use there are plenty of lines in K-space. So undersampled K-space is how the AI fasten the images is that the um, the lines which we acquire in the K-space is half. With the half information you provide that to your AI model, it will give you the full whole images. So there are different approaches, like you can give the image and then you will get an image. So the AI model works in the image domain as I showed before. And then there are K-space. K-space model, like you use the Fourier transform and then you get a Fourier transform image. End to end is like both image as well as K-space. You can give any type of input to the AI and it will give you that images. And different optimization you can use, like optimization tool inside the AI is, for example, in Unrolled, it uses the iterative, means the traditional method, and also it integrates the deep learning networks into the iterative model. And then there are generative model like GAN, which can speeden up. It can be more better than iterative model. So these are different examples of AI. Now let's come into UNET. Different architectures used in the cardiac imaging is, so UNET is kind of a backbone to MRI, and it is contracting path. Like for example, it takes the spatial features and also retains the resolution and keep the images reconstructed more realistic. So unit architecture consists of different components. One is encoder and decoder. So what encoder does is your images, it for example, if you give K-space or image, it reduces the imaging dimension into different vectors. Like for example, um, it changes from reduces the imaging resolution from 572 to 568, and it keep each step reduces the imaging resolution, and it is a feature extraction step. And then there is a decoder. Decoder, what it does is it takes all that information and reconstruct into original imaging space. And what you can do is one of the advantage of UNET is you can skip the connection, and then if you skip those lines, you will still get those reconstructed images. So what is the strength of UNET is it is both global and local information is retained, and it is very ideal for like for example, if the image is very much blurred, then you can use UNET to make it more super resolution. Then next commonly used architecture is generative adversarial network. So in this, it consists of two modules, that is generator and discriminator. So generator enhances the MRI using less number of case space, and then discriminator is it it discriminates between the real and also the corrupted case based data. So if you give an image and then you corrupt, if you give a corrupted case space, if you introduce noise into the case space, then it reconstruct using the traditional model like compressed sensing, and then you provide those input into a generator, and then it will correct for that motion. And it is very useful for cardiac MRI, where it removes the artifact motion correction, and also it reconstruct from sparse data, in the sense case space data as well. So you can give input image as well as Fourier transform case space as well for GAN. Then comes another architecture which is commonly used, unrolled model based network, where you are iterating the deep learning network uh, many times. So you can see here iteration 1, 2, and this iteration consists of regularizer and data consistency. Each module has different learned regularizer and data consistencies, and different benefit is that it retains the uh, pathology. It doesn't change anything in the image, so it retains the uh, physics informed structure, means it retains the image features, and it is faster, and also it has less iteration compared to the traditional method. Another network is variational network. It is unrolled. The only thing is they use different optimization algorithm like gradient descent for speeding up the iteration between the operation. So how it works is, for each iteration block, it has same regularizer and data consistency, and uh, this regularizer uses CNN based filtering based on the training which you had done, and also data consistency, it measures the case space data. So um, if you give imaging space, it will convert that imaging space into case space, and then it may it can measure, it can apply the CNN based filtering, and then again there is a case space data you can see here. You can also put image as well as case space, and then get into um, uh, the iteration block like regularization and data consistency, and it keeps on iterating, and then you get a case space, corrected case space, and then you convert into inverse Fourier transform into an image. So another emerging technique is transformer based uh, networks where you uses attention mechanism. So there are different methodology like swine transformer, which is being used widely for enhancing an image with less information, and you can get more benefit from attention is that the for example, it calculates the relation between the pixel which is far uh, distant from one pixel to another. It uh, calculates the relation between one pixel to the distant pixel, and it iterates based on that transformer. Benefit of this is that you can accelerate this the reconstruction in a faster way with transformer based networks. So at the end, in the summary, what unit is, it's fast, robust, and also it is limited to the it doesn't reconstruct some other fake images. And GAN is also similar. It retains the texture of the original image. One of the disadvantages, it's difficult to train. Unrolled is that it is physics informed. It means it retains the image intensity, and also it can be interpreted easily. Transformer uses both global and local information, and disadvantage is that it's very heavily computation is demanding. And then variational network is it preserves the pathology, means like unit, it is able to preserve the image information. Now let's come into the application. What we do is in this clinical application, we do motion correction, especially in the arrhythmia patient where the heart rate is different. AI enhanced perfusion imaging. Perfusion imaging is nothing but we are calculating the blood output using different method. Then comes late gadolinium enhancement and different contrast of MRI, where you can reconstruct the image with less information and get the image in a faster trend. There are different imaging contrast which we can use for different cardiac pathology. Now let's take an example where a patient is suffering from coronary microvascular dysfunction. What is CMD? Is that the the blood supply into the heart muscle gets restricted. So you can see there is a plaque formation inside the blood vessels, which is providing the blood to the heart muscle. So so you can see that it it might affect the microvascular, in the sense the capillaries have become less. The dimension of the capillary becomes less. So what happens is that there is less number of blood getting into the cardiac heart muscles. So then what happens is the cardiac contraction and relaxation reduces, and it affects the heartbeat, and then the patient eventually suffer from heart attack. um, it is very much prevalent in women. So we we are using these tools, the MRI tool, non-invasively. Usually to detect the CMD, there's a lot of invasion, like they inject contrast and stress. They also inject stress. What we are trying to do is, without all that contrast and the stress agent, we are able to detect this CMD. Another important imaging is CNA imaging. CNA imaging images different heart cardiac phases, contraction and relaxation. What is the application of AI is it helps us to calculate wall motion, strain, and also the ejection fraction. So ejection fraction is how much the heart is pumping the blood, and the strain is the amount of strain into the cardiac muscles. It's easily calculated through AI. And you can also do the acquire those videos in very less time. And also, as I said in the earlier presentation, the patient has to hold his breath. Then with AI, the patient need not hold his breath. He can just simply lay on the uh, bed. Another application is perfusion and late gadolinium enhancement, where the AI model enables full cardiac coverage. Within a second, you can acquire different slices. I mean, different view of the cardiac within a second. So in this image, what you can see is that this is the myocardium surrounding the left ventricle. It is more thick, and that's why we image this left ventricle region. So you can see that the enhancement is higher in this region. That shows that there is some issue in that region where it's called as scar. The heart muscle has is weakened and it has more fibers, so it's called as fibrosis. And it also, you can see the quality of the image is very much improved with the AI. And there are different contrasts like D1, D2, and also different mapping. So you can see different contrast. This is the blood pool. You can see this is the blood pool, which is darker in nature, and the surrounding heart muscles is lighter in nature. So you are able to appreciate the heart region in a better way. This one is a different contrast, LG, where the blood pool is more uh, prominent, means you can see the blood pool in a better way, and the heart muscle in a opposite darker intensity. T2 and T1 mapping in the sense where we acquire those images in different time points, and we apply different optimization algorithm like least square to calculate those T1, T2 mapping. And these are different maps where ECV is nothing but it's the inverse of that T1 images before contrast and after contrast. So we calculate those. So practically how we use is that either you can give fully or undersampled data or both together as a training data set. And then also you can give synthetic data, like you can generate a data and then give as the training data. And there are different loss function which we use, like L1 norm, L2 norm, per perceptual means how realistic you need that images, then similarity index SSIM, and then adversarial as a loss function. And also you can use hybrid loss, where you can use L1, L2, SSIM, perpetual together to get a better accuracy. And physics-based constraint is that you apply the mathematical equation to, like, for example, how do you get an case space into imaging space? That is a mathematical equation which you put into the uh, uh, training data set, and then you can get a more realistic images. Now, how you are able to get the freely available data sets? You can get there is called as fast MRI, where there are more than lakhs of images. It consists of knee and brain images. CMRX Recon and CMRS Recon 2024, these are used for modeling, a training data set foundational model, where it has different vendors as well as different imaging contrast also available here. And STA-COM, where there are different set of images where it is used for segmentation and reconstruction challenges as well. Now comes the challenges. What happens is that during the training, there are different data sets you have from different vendors. For example, people use Siemens, Philips, GE, MRI machines, and you need to have variety of images from those different machines. And we have different field strength in the sense the magnetic power. For example, 1.5 Tesla and 3 Tesla are very commonly used for cardiac MRI, and different pathologies. So you need to also add in different diseased cardiac images so that the model knows, okay, this is how the pathology contrast look like. For example, this has a pathology that if you put in your training data set, then it helps the AI model to get more realistic images. Then the other issue is that you need to label the data, and it is difficult to do unsupervised learning. Uh, it is more widely available that your data needs to be labeled. And then robustness to the arrhythmias, we are still in getting good quality data for irregular heartbeat. Irregular heartbeat with motion and noise. And another is the regulatory. So you need to undergo regulatory. For example, in US, you need to get FDA approval for any software-based, uh, like for example, AI. You need to undergo the regulatory module to be used in the clinical uh, domain. And also we have in medical imaging has variety of modalities like CT, MRI, PET. So to use different type of images as a training, then it becomes more better for a training reconstruction. And then integrating it into clinical decision system, which is also very much demanding. We have lot of AI based reconstruction, but most of them are still in regulatory approval. So there's another limitation. And also another limitation is that AI tends to generate fake pathologies as well. So we need to have a better way that the clinician is able to validate those regions. So we are not fully into it that the clinician or radiologist needs to approve those images. In conclusion, AI, as I showed in the graph, dramatically reduces the acquisition time, preserves the diagnostic quality for certain images, and also we discussed about different architectures like unrolled, generative, transformer, variational network, and these are very much motion robust, real-time images. In future, what we need to do is we need to have a variety of data set having different features and foundational model, and as well as integrate into clinical domain. Thank you everyone for listening. So we are open for question.
Participants, any questions, please, or we can start the discussion related to this her presentation and all. Any question, please type in chat box or you can unmute and ask her.
Yeah, there's one question, how we can decide best model. So actually what we need to do is the best model can be decided by the way you train the model. So more number of variety of images you give to the model, it becomes more robust. So in that way you can decide, you can use any architecture. Yeah, for example, I have also have a slide where there is a limitation, like for example unit, it tends to detect like different voxels which is not in original image. So unit suffers from the disadvantage that it predicts different voxel which is not present in the original image. So uh, uh, best model how we can get is to first of all give variety of training data, how well you are trained the model, that is called as foundational model. Yeah. And also you can calculate different metrics like accuracy, sensitivity, which is present in the literature, and based on that you can use those models. And then how do we get public data set is I gave a table. So these are the publicly available data sets like fast MRI, CMRX Recon, STA-COM, and then CMRX Recon latest last year they had released different data, which these are all open source. You can also use open source tool like BART, BART, BART. It is openly available for reconstructing MRI images. Is there any other question? Thank you. Uh, Thank you for the questions. Yeah. Hybrid model are effective than single one. How can we create a hybrid model? Okay, yeah, hybrid model, like for example, you can see, uh, for example, transformer-based model. It is nothing but different model like unit and CNN together. You can use those hybrid model. One of the issue with the hybrid model is the model becomes complex. It becomes complex for you to predict the images. Yes, hybrid model are effective than single, but disadvantage is computationally demanding as well as complex to train.
Actually, I have one more one question regarding
Yes.
related to this one. Yeah. So, what are the current trends in this area? Can you share something related, or we can discuss something related to that current trends, and what are the difficulties you are facing when you are using these kind of models and other things in your research area, like AI applications in the cardiac imaging? So, can you explain or give some idea about that also? I think that will
Yeah.
be helpful for us.
Okay, so current trend I have already discussed. So different architectures which is very commonly used in cardiac imaging is UNet, transformer based, and also GAN based models, which is very much commonly used. And another is that the limitations. Can you repeat the question, sir?
No, I just curious about what are the trends coming in, and what are the current trends in your area, like your research area, and what are the problems you face during this implementation and all. what is the requirement for fulfilling all these kind of things. So that kind of discussion, I think I
Okay.
expect from you more on
Oh,
that.
yeah. So one of the main current trend is in the cardiac MRI is that the images are more affected to the motion, and then there is another thing is that you need to acquire the image in a faster way. For example, the current protocol takes around 30 minutes, and it becomes very difficult for the patients to be lying on the MRI table for a long time. And as well as another issue is that the patient is having issue holding his breath. So current trend is in the AI image reconstruction is that we are doing free breathing. So we are telling the patient to freely breathe, not to not hold the breath. We acquire multiple images one at a time, and we give those multiple images to AI to reconstruct within 1 to 2 minutes. And another way is also segmentation based reconstruction. So you are giving different view of that image, and then it is able to generate different phases like systolic and diastolic within like 30 seconds.
Yeah.
And
Okay. Oh, yeah. Go ahead.
And the problem which we face is that the amount of training, uh, like as compared to China, the amount of data which we get is very less. Like in China, you can get 10,000, 20,000 images within 1 day. So that much they acquire the data. So in India also, we can generate those images. But the thing is, we need to have a platform where we are able to upload those images and people can use those images to create foundational models.
Yeah.
And it can be readily available, and different models can be used to predict uh, disease pathologies.
Yeah, I just add to one more point. Like you suggested like around 30 minutes for a patient for scanning. So that's also a difficulty. So
Yeah,
my thinking is what about the newly coming that 0.55 Tesla Freemax from Siemens? Is there any advantage in these kind of applications? Like it reduces the scan time, obviously. What is your like advice, or what is your experience with those kind of
yeah.
machines?
So yeah, we do have high Tesla and modern scanner coming in. But the issue is the availability of those images, of those scanners. Like for example, in India, we can get 3 Tesla. And right now, it is widely available. 1.5 Tesla is more wider than the 3 Tesla. So we do have very high-end, like for example, Siemens, United Imaging, also having different AI-based reconstruction where you can reduce the imaging scan time to like within a second. Yes, it is currently integrated and also released into the current scanner. But the limitation is the availability. And
Yeah, yeah.
that's,
And one more thing is like India, you suggested like compared to China, India is also having a lot of
yeah,
data, and
yeah,
they are available or they are available in our scanners or in our like the storage settings.
correct.
Yeah,
Yes,
but we need a protocol, or we need a standardized form or storing or developing model, and for training purpose, it's like a huge process. Like we required a group of people and do all these
correct.
people.
Yes,
Yeah, yeah. It's good when we are coming together and do processing together. Then maybe in these images are more useful for the research purpose. Then it will give a good good results, like a good model and good results,
Correct.
good observation.
Yes.
Yeah, coming from.
Yes.
Yeah, that
Yeah.
actually in India started. I think the ISMRM parties also they are
Yeah.
actively participating all these kind of activities. I think maybe
Correct.
in
Yes.
future we will get more insight into that.
Yes. I also agree with you that we need more public data set, not only from one part of the region. For example, FAST, MRI, CMRX are from one part of the region. Uh, for example, for brain imaging, we have variety of data set from different part of the world. For example, there is a platform called as ADNI, ADNI, where you can get it's publicly available. You need to make an account and you can get plenty of different variety of diseased images of the brain, and as well as you can get healthy subjects as well, healthy subjects brain images, and different contrast of MRI also is available there. So people here in this platform can see those ADNI. And also for cardiac images and knee images, you can use this publicly data set which is listed here.
Yeah, I think these participants also they are interested to know
Yeah.
from where we get the images. For we are ready with
Yes.
processings and we have the pipelines, but from
Okay.
where we test and where we use the gold standards, all these kind of questions coming from the participants in the I think the last 2 days. So these kind of public data
Oh,
set to give the information, it's good for them. But in yeah, in addition to that, I ask like in India is do you know any these kind of public data set repositories or like any other platforms?
no,
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 no.
there is no public data set from India. There might be, but they are collaborated with the US, but they are not openly available.
Yeah, any from Nimhans or any platform like IAC
I'm
Matching?
not aware of.
I'm also
I'm
not
not
aware.
aware.
Yeah, but
I
almost
don't
all
think
the
from India
public,
we have. Yeah.
yeah, all the public data set is available Europeans or from the US based things. Yeah,
Europe and US as well as China. China,
China. Okay.
Chinese the CMRX recon is from those
Oh,
subjects. Yeah.
oh, okay. Yeah, that's good. Any other questions from participants related to this cardiac MRI and reconstruction algorithms and AI applications, please? Otherwise, you can stop. Safer, please.
Thank you, ma'am. Thank you very much we are truly grateful to you, ma'am, for your
Yeah.
insightful session on artificial intelligence in cardiac image reconstruction. Your
Thank
valuable
you.
expert Your valuable expertise and clear explanations have given us a deeper understanding of how advanced imaging technologies can transform cardiac diagnosis. Once again, thank you, ma'am. We are truly appreciate the time and effort you dedicated for sharing your knowledge with us. Thank you.
Thank you very much, Saifa and Dr. Rafiq sir, for inviting me for this lecture and providing me this platform. Thank you very much.
Thank you,
Thank
Archana. Thank you so much.
Thank you.
The feedback form is now open. I kindly request all participants to complete it at the earliest.
And one more thing, now the first session is over and we are planning to take a group photo. So if all participants are available, then you just on your videos and we will take the photographs. Yeah, thank you. Suraj, yeah. Yeah, please open for let's say 30 seconds or something, then it will be good for us. Okay, thank you. Thank you all.
Thank you, sir.
So next session we will start around 7:30. Um, so is there any questions or something you can ask? Otherwise, we will see around 7:30.
Sir, is it audible?
Yes, sir. Yes, sir. Yes, sir.
Okay.
Saifa, we will start.
Good evening and welcome to day 3 session 2. After an insightful discussion on AI in cardiac image reconstruction in session 2, we now move on to our second session of the day. Our today's topic is human emotion detection using physiological signals. And let's welcome our esteemed speaker, Dr. Ansar SM. Let me introduce Dr. Ansar SM. Dr. Ansar SM is a senior IEEE member, received his BTech in Electronics and Instrumentation from QSAT, ME in Applied Electronics from Anna University, Chennai, and honored his PhD from NIT Calicut. He is currently a faculty member in the Department of Electronics and Communication at TKM College of Engineering, Kollam. His research areas include medical signal and image processing, pattern recognition, biometrics, AI, and engineering education. Dr. Ansar is a recognized research supervisor under APJ Technological University and is presently guiding around 4 PhD scholars. He is actively associated with several professional bodies, a senior member of IEEE, a member of IEEE Signal Processing Society, research activities chair of IEEE Education Society of Kerala chapter, and member of AICTE. On behalf of KMEA Engineering College and all of us, welcome you, sir, for the session.
Hello, is it audible?
Yes, sir.
Yes,
Okay,
sir.
thank you, Saifa, for the detailed introduction. Rafiq sir, can I start the session?
Yes, sure, sir.
Okay. So is the screen visible?
Yes, sir. It's visible.
Okay. Okay. So today I'll be talking on human emotion recognition using some of the body cues such as speech, EEG, and facial cues. Sir, is the sound audible and the screen visible? Everything fine?
Yes, everything is
Oh,
fine, sir. Please
okay,
do it.
okay. So, I think this is the second session, um, but I will try to make this light. Okay. Uh, since you have completed one session, and what I'm planning for today evening's discussion is uh, to bring you some flavors of this wonderful area of human emotion recognition. Okay, and we will see some of the applications and some of the use cases in this domain, and what are the fundamental theories of emotion, and mainly we'll be concentrating on either one or two. If possible, we'll try to cover three. This speech-based emotion or EEG-based and facial emotion recognition systems. Also, we'll talk a bit about multimodal fusion techniques and what are the research challenges and ethical consideration to be look into in this research domain and the future trends and research directions. Okay. So, without wasting time, we all know what is an emotion is. Okay. It is a complex psycho or physiological experience involving feelings, expressive behaviors, and arousal. And in the introductory session, it was told that human emotion recognition due to actually, physiological means it should be related to some physiological signals. So it should not be the correct title. The correct title should be we will consider physiological signal, which EEG is of course a physiological signal, Heart rate is another physiological signal, but we'll be talking about some behavioral signals also, that is facial expressions, speech tones, gestures. These are all behavioral features which depends upon or which captures the emotion of a particular person. Moreover, the mental process involved in acquiring knowledge and understanding, that is cognitive. So these are the key components which are coming under emotions. So we'll be mainly focusing on physiological as well as the behavioral aspects of emotion. That too, EEG, face and speech. We will try to concentrate on that if time permits. We will cut short. Okay. So, and why emotion recognition? So, it bridges between human psychology and computational intelligence, and enables machines to interpret and respond empathetically. And there are different applications or use cases for emotion recognition. While we're discussing that, we will get more into why this emotion recognition is important in today's era. Okay. And number one is in healthcare, mainly for mental health monitoring. For example, early diagnosis or neurological disorders, for early diagnosis and neurological disorders. And similarly, this type of techniques can be used for to see how much improvement is there in the therapy and in rehabilitation schedules. And it is also used, it can also be used in education at large. So for example, the example is an e-learning app adapting the content of the studies if the student looks frustrated. Okay. And another one is human computer interaction. A best example that I can give is the virtual assistants and chatbots detect user frustrations or satisfaction and respond more empathetically. And another one application is security application, where we can we can identify suspicious or aggressive behavior in airports, railway stations, stadiums, banks, etc. Okay. And also in marketing, we can also use this in marketing. And also we can detect the stress, anxiety, or inconsistencies in security application. We can detect the stress, anxiety, or inconsistencies of a particular person through their voice, physiological cues, or through facial micro expressions. So all these are some of the use cases where this emotion recognition can be used. And now coming to the modalities of emotion recognition. Okay. If it is speech, the prosody of speech, pitch, intensity, rhythm, etc. These are some of the features we'll be mainly concentrating on. And you might be knowing that prosody is nothing but the melody and rhythm of speech that help convey emotion, emphasis, and meaning beyond the words. It emphasizes the meaning beyond words. That is what is called prosody. It is simply the melody and rhythm of speech that helps convey emotion and to emphasize something beyond words. And pitch, we all know that it is the intonation, that is the rise and fall of voice. And intensity is nothing but the variations in volume to indicate the importance or emotion. And rhythm is nothing but the timing or tempo or the pace of speech. So these are the features we are mainly interested in emotion of detection from speech. And coming to the EEG, it is the brain activity. Brain activity, normally we'll be taking the EEG signal itself, the electrical activity of the brain. And then coming to the autonomic signals. Autonomic signals are examples like heart rate variability. Autonomic signals, in the sense, it is a physiological responses controlled by the autonomic nervous system. So, for example, heart rate variability, skin conductance due to sweating. Actually, the skin conductance due to sweating increases with emotional arousal. So, skin conductance can be considered as one of the marker of increased emotion. So, all these are coming under autonomic signals controlled by autonomic nervous systems. So, for example, heart rate variability and skin conductance. And coming to the facial cues, it contains expressions and micro expressions. Expressions, we know that it captures general conscious emotional state of a person. Say, for example, we are laughing or we are smiling. Everything will be captured. And what is the difference between expressions and micro expressions? And in most of the emotion recognition systems, we are interested in micro expressions than expressions. And and these micro expressions are hidden informations, actually, because most of the psychologists and the policemen, they are interested in more interested in micro expressions than expressions. And micro expressions capture true hidden or suppressed emotion valuable for lie detection, security, etc. So, for example, expression, I can give you an example for expression. For example, smiling when happy, frowning when angry. These are examples of expression. And I can give you some example for micro expression. An example for micro expression is a flash of fear before forcing a smile. A flash of fear before forcing a smile. And another one, a micro frown when hiding anger. So, so these types of emotions, these types of hidden emotions, if we can identify that, we can correctly identify the emotion of a particular person. So these are coming to the facial cues, expressions and micro expressions. And another one is multimodal fusion. Multimodal fusion is combining more than one modality to improve the robustness of a particular system. We know that uh, uh, a system can be considered as robust if it continues to function well, even when the conditions are not ideal. Okay. So these are some of the main modalities of emotion recognition in the literatures. There are n number of papers available in research papers available in lot many research has been done in speech, EEG, face, and multimodal fusion. And now, why emotion recognition matters? Why emotion recognition matters in AI and human computer interface? The first and the foremost thing is the gap in traditional AI. Most of the current AI focus on what we say, but misses how we feel. It misses the emotion. So nowadays, most of the recent works are coming in this direction to incorporate the emotion as well. So, for example, chatbot may answer queries. At present day, chatbots may answer queries, but fail to detect user frustration. So if we can, it will be good if we can develop a chatbot which also can detect the frustration of a person and give the query according to that. Okay, so human-like interaction is required. True intelligence is requires understanding non-verbal cues such as tone, expressions, and physiological uh, signals. And the second reason is the rise of effective computing. So now the question is, what is effective computing? So effective computing is coined by a professor at MIT, and the effective computing focuses on systems that can recognize, interpret, process, and respond to human emotions. It is a system, AI system that can recognize, interpret, and process human emotions. Okay, so such types of research are going on, and moreover now we have advanced deep learning models, like we are using advanced CNNs for face recognition, LSTM machines for speech recognition, and transformer models for classifying EEG or physiological signals. And moreover, there is an increase in demand for personalized AI. Personalized AI in the sense systems tuned for a particular user, which is widely used in healthcare, education, mental health, customer service, and human-computer interactive devices. And this is an interdisciplinary field which combines computer science, psychology, and neurosciences. So a very interesting area. And now let me point out some of the research potential in this particular area, or the future directions that most of you can think about. The first one is bias reduction. So addressing cultural differences in emotion expression is still an unsolved issue. Cultural differences in emotion means a person in the East that from Asia and a person from the West, from California or in USA. So, so there will be some bias in the systems. So these bias reductions, these emotional, there will be some minute differences in their emotional expressions based on the cultural differences and ethnicity of the people. So this bias, so there is a huge bias in the systems. So the bias reduction is one area where we have to focus on. And the another area is multimodal emotion recognition. I have already told you the fusion of speech, facial, EEG, or physiological signals. Also, the real-time systems. We need more real-time systems, that is emotion-aware assistants like chatbots and robots and any other interactive platforms that can work with emotion aware in a real-time system. And another one area is explainable AI, where explainable AI, you know that AI is designed to make its decision and predictions transparent, interpretable, and understandable to humans. And most of the AI systems now work as a black box. Okay, we are feeding some input, we are getting some result, we don't know what is happening inside. Okay, so the explainable AI. So we need more systems which are transparent, because the emotion recognition models require the ethical clearance, and it should be transparent. So the AI system should be designed to make its decision and predictions interpretable and understandable to human beings. And another thing is cross-cultural expansion, that is multilingual in the case of speech. We have only less number of speech recognition systems that works for Malayalam language. Most of the speech recognition systems or emotion recognition based speech systems are designed for the English speaking people, because most of the databases are available with that language only. And also the cross-cultural adaptability. I was mentioning about the in terms of other emotions, in terms of so cross-cultural adaptability in the sense different cultures, they will be representing their emotions in a slight different way. There will be small changes in those emotions. So considering all these things is the cross-cultural expansion. Okay. And now coming to the key applications of emotion recognition is number one, I told you the mental health diagnosis. Okay. So the problem is traditional diagnosis relies on self-reports, which are subjective, or clinical observation, which are time-consuming. And the AI solution is the speech analysis. So, for example, detect depression from voice biomarkers. Okay. So, for example, AI analyzes voice for depression risk, and EEG or facial recognition system identify anxiety or PSTD from brainwave pattern. What is PSTD? PSTD is the PSTD, post-traumatic stress disorder. Post-traumatic stress disorder. So identifying anxiety and this post-traumatic stress disorder from brainwave patterns. So all these are some of the examples where this can be applied in mental health diagnosis. Okay. And another one is affective computing in human computer interface. The goal is make technology adaptive to user emotion. Some of the examples I can cite is stress detection. So for example, car adjusting music or lighting if driver is angry. One example. In gaming, we can use this. So for example, dynamic difficulty adjustment based on players' frustration. Okay. And in coming to education, personalized learning, there are a lot many companies, edutech companies working with emotion-based learning, incorporating how to incorporate these emotion feelings to enhance the education and feedback. Okay. So the challenge here is online learning lacks face-to-face emotional feedback. Now what is happening in this class? Online learning lacks face-to-face emotional feedback, and the solution is facial engagement tracking. So for example, camera, if there is some camera which detect the confusion or boredom of a participant, and the teacher or the presenter can change his presentation accordingly. And similarly, voice analysis, tutors can adjust their pace if students sound uncertain, or if the students seems to be not understanding the concept, if they are missing some concept, by seeing their face or by seeing their eyes, the faculty can follow by seeing the eyes of the student that whether he is or she is following the course. So by using these emotions, the appearances, subtle emotions, we can change the personalized learning or teaching learning process. And coming to the marketing, so I forget to give an example for marketing. Okay, in customer sentiment analysis. Okay, industry needs 60% of the customers abandon brands after poor service, that we know. So we can by using the customer feedbacks or some customer surveys based on their emotions, based on their response, we can analyze how to improve the product for customer satisfaction. So all these things can be can improve the marketing strategies. Okay. And another thing is neuromarketing and BCI, where neuroscience meets AI. So, for example, EEG headsets measure ad engagement versus brain waves, and facial coding predict purchase intent from smiles or surprise. If somebody neuromarketing in the sense, if somebody is smiling, based on the smiling, the marketing person can change his presentation styles, or like that he can. So that is what is called neuromarketing. So all these things are nowadays coming into practice. Okay, so these are some of the use cases. So I'm giving you some of the research area where you can think about applying these emotion based recognition. So the open challenge in this domain is, I told you, is the bias. Model trained on Western faces or voices fail for global populations. So for the model trained for West may not be equally performing well for the East. So for example, a face recognition system which works well for white faces will give poor result with black faces. Okay. And privacy, EEG or facial data is highly personal. So how to anonymize? So that is a problem. And real-time processing, latency issue in multi-model fusion is another issue. And research direction for academia, the cultural application, collect diverse emotional data sets. We need to collect diverse emotional data sets. Most of the work they are focusing on single emotional data sets. And I already told about explainability of the model. Okay, we need a more explainable model. And another important thing is, you see, the problem with the present research is, and I hope electronics and electrical engineering graduates will be here in this presentation. So my suggestion is, most of the AI ML works end up in simulation only. Simulation, they will be creating a better model, writing a paper, and that's all with that. But in hardware, it is very difficult to get papers of AI and ML which can work on edge devices. So my request to the electronic graduates or the students or the faculty who are in the electronics or in the electrical domain is, we need to convert these papers which are in Python or in MATLAB to a realizable hardware by using some STM. There are new STM boards are available. Jetson Nano boards are available. So we have to work with these type of hardware devices so that we can convert our papers into a real-time workable hardware models. Okay, so that is one of the challenges we are now facing, because AIML is only now in papers. But in hardware or the product in hardware, especially in academia, the companies are doing, but especially in academia, we need to deploy the lightweight models on mobile or embedded devices. Such sort of works are lacking. So that is one area where you people can focus on. Okay, so I can say that the emotion AI is still in its infancy, and converting this real theoretical work into hardware is still in its in the baby state or infancy. Okay, and now let me quickly introduce some of the theories of emotion. So mainly emotions are explained through multiple psychological theories, and these theories help us to understand how emotions originate and how they are expressed. And two main categories are there. One is the categorical theory, which deals with discrete emotions. Discrete emotions in the sense anger, joy, sadness, etc. Discrete emotions. And the second one deals with dimensional theories, the emotions in continuous space. For the time being, you won't understood what do you mean by emotions in continuous space, but once I enter into that, it will be clear. An example is valence arousal model by Russell's circumplex model. So these are some of the theories, 1, 2, 3, 6 theories named after these great gentlemen. So let us consider each one. James Lang theory. Okay. So James Lang theory, it says that emotions arise from physiological responses to stimuli. I repeat, emotions arise from physiological responses to stimuli. So that is first thing, when we have a stimulus, there will be a physiological response. And once there is a physiological response, after the physiological response, an emotion will be coming. An example is angry dog barking. So that is a stimulus. So when we see an angry dog barking, our heart rate increases. So that is the first physiological response, what is happening. So when the heart rate increases, fear arises. So that is a simple example for this James Lang theory. Okay. And the second one is Cannon-Bart theory. And what the Cannon-Bart says is emotion and physiological responses occur simultaneously and independently. So these are the historical changes in the theory. Cannon-Bart says that emotion and physiological responses occur simultaneously and independently. So for example, when we see a dog barking, okay, simultaneously there will be a physiological arousal. So for example, increased heart rate, and at the same time the emotions are generated. So that is the so this concept is used in multimodal fusion. For example, combining multiple signals, body signals and emotions. So this is the okay. So this is the concept. Activation of a specific region in cerebral cortex, especially the thalamus, and it causes, the stimulus causes both physiological responses and emotions. And the third theory is two-factor theory, okay, by the gentleman Shatter Singer. So according to this theory, emotion, he introduced another one concept. Emotion is based on physiological arousal and cognitive labeling. That is, the cognitive labeling is also coming into picture. So he mentions that emotion is based on physiological arousal and cognitive labeling. So for example, the same stimulus, dog barking. So at that time, physiology, there is a physiological arousal. Okay. And physiological arousal leads to cognitive labeling. So based on the physiological arousal our heart beats fast. So at the time, there is a cognitive labeling, there is a mental labeling. The person starts to label, oh, that is scary. And this cognitive label and physiological arousal, or the cognitive label which is followed by physiological arousal, leads to a particular emotion. Okay. And the other one is appraisal theory. Okay. And the core idea is emotion arises from cognitive appraisal of a situation. Cognitive appraisal of a situation. Emotion depends on how we evaluate a situation. It is not what happens, but how you interpret it. That is the core idea behind this appraisal theory. It is not the event itself, but how we interpret and evaluate it, that shapes our uh, emotion. So that is what is called this appraisal theory. Okay. And the another theory is Ekman's basic emotion theory. Ekman told that emotion can be classified into 6 basic universal emotions. So these are the 6 basic universal emotions which are widely used in face-based emotion recognition systems. Say for example, anger, disgust, fear, joy, sadness, and surprise. So these are the 6 Ekman's basic emotions. And the last one is the dimensional theory, or the valence arousal theory. And valence, uh, this theory restricts emotions in a continuous 2D space. Valence means it is a pleasant emotion. Arousal is an excited emotion. Valence is a pleasant emotion, and arousal is an excited emotion. So this is the valence and arousal model. Okay, with all the emotions are mapped into this 2D space. X-axis is the valence and the y-axis is the arousal. So here there are 4 quadrants. The first quadrant represent happy. Okay, and based on the value of valence and arousal in the first quadrant, happy can be again divided into delighted, excited, like that. And in the second quadrant, it is angry. Based on the values of valence and arousal, it can be classified into tense or frustrated. And sad is in the third quadrant. Based on the values, it can be classified into bored, depressed, etc. So these are some of the theories. Okay. So this valence arousal model is widely used in EEG based emotion recognition systems, as well as in speech recognition systems and EEG recognition systems. Some of the speech and EEG based recognition systems works on this valence arousal theory. That's why I cited this theory. And now let us discuss a case study with speech-based emotion detection system. So actually, I'm presenting one of the work of my MTech student. Okay. Speech-based emotion recognition system. Actually, he made a transformer model for classifying speech emotion recognition system. Okay. And in the introduction section, I told you some of the emotional cues in speech are tone, pitch, Pitch, I already mentioned the rise and fall of voice. Intensity is the variation of variations in volume to indicate importance of emotions. Okay. So tone, pitch, intensity, and rhythm are some of the features we used. And this is widely used in human-computer interaction, virtual assistants, customer service, mental health monitoring, etc. So previously we were using handcrafted, early we were using handcrafted acoustic and prosodic features. Prosodic features in the sense the melody and rhythm. Prosody means the melody and rhythm of speech that helps convey emotion, emphasis the emotion and meaning beyond words. So that is what is called prosodic feature. And today modern devices, deep learning models are used, CNN and RNN transformer models are used for feature extraction. And the transformer-based models captures contextual and temporal patterns, boosting accuracy. And the challenges in this area is speaker variability and background noise, cultural and language diversity, which I was mentioning earlier. And there were different models. Some people used ResNet 101 CNN and deep BiLSTM models. And these are some of the database. EmoCap, Korean speech emotion dataset, EmoDB, and EmoCap, EmoDB. These are some of the database, are some of the databases which are widely used. And we have employed RAVDES dataset. RAVDES dataset is another dataset which is widely used for EEG-based speech recognition. Okay, and most of the systems are getting performance up to 70, nearly 72, some 80, 85%. Some models are getting 90% as well, more than 90% as well. So EEG-based emotion recognition. So the main literature gap in this area is which will be helpful for your future research and all. So the lack of multilingual and cross-domain evaluation. So that is one of the main limitation in this domain. Okay, and most models are trained on single language datasets and poor adaptability across accents, cultures, and domains. So that is the actually the thing is we lack such a database. If a data set is available, people will try to work. Actually, such type of databases are lacking. Okay, so we need data collection in order to incorporate these type of researches, and need for real-time and lightweight models. So most of the models are using 3D CNN, BiLSTM, transformer models, which are very heavy. In order to employ this device, these type of models in edge devices, or we need lightweight models to incorporate to work with edge devices. So we need lightweight models to reduce the computational complexity for hardware implementation. So not suitable. So present day models, most of the models are not suitable for real-time deployment because it contains millions or billions of parameters, because heavy large models, and underutilization of pre-trained audio language models. Actually, there are audio language models, very famous audio. I have cited here two very famous audio self-supervised audio models, and two such models are Wave2Vec and Hubert. These two models, and these two models are rarely used in, even though it is used for speaker identification and speech recognition. These type of models are not seen that much in human emotion recognition system. And if we can utilize these two models, it could boost the performance, and we can employ these models in low resource setting as well. The another thing is emotion overlap challenge. Similar emotion, it is very difficult to classify or separate similar emotions. Say for example, happy versus neutral. For some people, if they are happy, and if some people they are neutral, it appears to be same. Okay, so it is very difficult to classify similar emotions. So there also we need some technical expertise. And fear versus surprise. So fear and surprise. Some people are showing these two emotions in the same fashion. So it is very difficult to differentiate between fear and surprise because they are often misclassified. So it requires so these type of, in order to classify these type of emotions, we require fine-grained feature learning. Okay. So actually, in this work, we have considered 4 features. MFCC is the MEL frequency substral coefficients, MFCC feature. Okay, and then we have considered, and MFCC captures speech features based on human auditory perception. So MFCC is widely used in speech and speaker recognition. It captures speech features based on human auditory perception. And another one feature is the Tonnet's feature, tonal centroid feature. That is the Tonnet's feature. It represents the harmonic relationships. So for example, chords, keys, etc. in speech. It is widely used in music in music for emotion or genre analysis. So tonnet feature is also we have considered, and we also considered the chroma features. Chroma, actually the chroma maps audio into 12 pitch classes. These chroma features captures harmony and melody from speech. So, and another one feature that we have considered is MEL spectrogram. MEL spectrogram features, and these MEL spectrogram, everyone knows that it is a MEL time frequency representation of speech or sound on MEL scale, and it shows how energy is distributed over the time frequency representation of the sound in MEL scale. So these 4 features we have considered, and we have employed a transformer model to capture the temporal dependencies. And I have said MFCC, if he takes what is being said, okay, and chroma, it represents how it is said, that it represents the pitch or harmony of the emotional cues. And here I have shown some examples of MFCC feature. So this is the representation of the feature in 2D. The first one is the MEL frequency substral coefficients capture the speech texture and are crucial for distinguishing emotional tones. And the second one is chroma features representing the pitch content across time, highlighting the musical elements in speech. If it is not musical elements, it maps audio into 12 pitch classes, capturing the harmony and melody of the particular speech sample. Okay. And Tonnet feature and the MEL spectrogram, and Tonnet's it captures the harmony and emotional tonality, whereas the MEL spectrogram it gives the energy of the signal in time frequency, the energy distribution of the signal in time frequency. And the left side shows the harmonic relations of the Tonnet's feature. And this is a MEL spectrogram. The right side shows the MEL spectrogram. It visualizes energy patterns across the frequency bands. And now what we have done is we have combined all the 4 features. So we have combined the feature maps by merging all the 4 features. And this is the image that shows the fusion of MFCC, chroma, and all the 4 features, which represents a comprehensive audio representation. Okay. Okay, so by fusing all the features, the model receives a holistic input leading to a better emotion classification accuracy. We told that MFCC captures the spectral information, chroma captures the pitch and tonal information, tonnets carries the tonal relations as well as the harmonic relations in speech, whereas the MEL spectrogram, it takes the time frequency energy distribution. So what are all things possible we have taken and we have concatenated and we have converted into a single vector in order to get better classification performance. Okay. And I already mentioned we have employed the RAVDIS data set, and this is developed by Ryerson University, Canada. Okay, and it contains the composition of the data set is it contains the speech of 12 males and 12 females, total 24 professional actors. The total it consists of 1440 audio speeches, and it contains audio only as well as audio visual as well as songs audio, and it contains 8 distinct emotions. Okay. So coming to the speech characteristics of the database, it was sampled with a sampling rate of 48 kilohertz, which is higher than the CD quality, which is 44.1 kilohertz, and encoded with 16 bits for precision. And this is how the speech samples are named. Each number signifies different things: speech, vocal channel, modality, emotion, emotion intensity, statement type. Statement type means what sentence they are uttering, repetition, they are repeating or not, actor ID. So based on this, the samples in the databases are named or labeled. And the advantage of this RAVDIS dataset is it's of high quality and noise-free recording, balanced across actors, genders, and emotions. And it is a standardized dataset widely used in speech-based emotion recognition research. But the only thing is it is slightly unbalanced. The neutral, we identified that the neutral emotion samples are less. Okay. So by using data replication techniques, we can improve the data balancing techniques. We can improve the size of the data set and standardize the and balance the data set. So this is the model architecture that we have used for speech emotion classification. Actually, initially we have done some pre-processing and all the features are extracted, and then by using the transformer model, okay, we have trained the transformer model, then test the model, and the 8 emotions were classified and the performance were classified. Performance were evaluated based on the standard evaluation matrices such as accuracy, precision, recall, and F1 score. So this is the workflow of the model. So I can show you this diagram. Okay, this is more, I think it is easy to understand. So first of all, we have a raw input converted into continuous vector representation. Okay, all the features, all the concatenated 4 features, after fusing, the dimension was 100, 159. where 100 represent the time step and 159 is the features. That means there are total 159 features and 100 represent the time steps. Okay. Then we performed some dimensionality reduction techniques to reduce the dimensions to 100, 128. Then we perform some positional. So all these are coming in input preparation. Positional encoding retains the temporal order. In the sense, we add information about sequence order, because transformer don't inherently knows the time order. So in order to give an information about the sequence order, positional encoding was performed after the data dimensionality reduction. Okay. Then we moved to the transformer encoder, and the size was reshaped. The size previously it was 100, 128. Now it was divided into batches. The inputs are divided into batches. So 100, batch size, 128. And the main components of the transformer model, here you can see this is the within the transformer model, we have multi-head attention, which captures the temporal relationships. And we had a feed-forward layer. And the feed-forward layer process features token by token. Token-wise processing is performed in a feed-forward layer. Then coming to the normalization and residual connections. Actually, the normalization and the residual layers, it stabilizes training and avoid the vanishing gradient. So that is the role of normalization and residual connection. Then we had we used two stacked transformer layer, which deepens the learning process. So we used the two layers or two stacked transformer layers, or two transformer layers were stacked together to deepen the learning representation. Then we performed average pooling, average pooling, so that the dimensionality is reduced. Then final linear layer. The final linear layer converts the reduced data to 8 different probability into the probability scores. So that finally we will be getting the probability score for each class. So this is the classification workflow. So the first one is the raw inputs are converted into continuous vectors. Then positional encoding is performed. Then multi-head attention. The model looks at different multi-head attention means the model looks at different parts of the sequence simultaneously and captures temporal and the contextual relationship between various features. And then coming to the residual connections to avoid vanishing gradient problem, normalization to stabilize training, and feed forward layer, which process features token by token. Then again add and norm. Add and norm is nothing but residual and normalization, which stabilizes training and avoid vanishing gradient. And then finally, we used softmax. Final representation is classified into target categories, normally into probability, into different probabilities, so that we can classify it into 8 different classes. So this is the performance. We have considered only 50 epochs. Okay. And this is the training versus validation performance. So the training performance and the validation performance. And this is the confusion matrix we obtained with this. So the key insight is the best recognized emotions are calm, sad, and surprised. Neutral, because high diagonal, because these are having high values in the diagonal. So that means there is minimal confusion, and most confused emotion is angry. It gives lower accuracy. For angry, it gives lower accuracy and scattered misclassification, if you can see in the confusion matrix. Overall model performance is very good with balanced recognition across most emotions, but require improvement in distinguishing angry from other emotions. So that is the results. So these are some of the numerical values based on precision, recall, and F1 score. And I hope the precision is nothing but of all predicted positive, how many are actually correct. So that is what the precision indicates. Of all predicted positives, how many are actually correct? So that is what precision gives. And recall gives of all actual positives, how many did the model correctly find? So that is what is called recall. So precision gives the correctness in classification, whereas recall gives the completeness in classification, because completeness in the sense because it gives of actual positives, how many did the model correctly find. So that is what is called recall, which gives the completeness in the performance of the classification. And F1 score is nothing but the harmonic mean of precision and recall. So this is an example where a simple example of this emotion recognition based on the transformer model. Okay. And the future scope is we need to develop a real-time emotion recognition for interactive and assistive application. Also to extend to multimodal emotion recognition by combining speech with facial expressions or text or physiological signals, and apply transfer learning with larger pre-trained models. Previously, I was mentioning about Wave-to-Vec and Hubert model, which is self-supervised model for improved performance. And another is enhance robustness to noise, accents, and cross-lingual variations, and deploy in real-world domains such as virtual assistants, call centers, healthcare, and education. Expand a data set to cover diverse languages, cultures, and nuanced emotions, and explore personalized emotion models tailored for individual user to improve sensitivity and adaptability. So these are some of the proposed future scope. So actually, this is the demo code. Okay, actually, we cannot run the code now because training itself, it will take time. Okay, just I will scroll. So what are the things we have used? The Librosa package, and the sklearn was used, and the feature extraction part, and TensorFlow, we have used the TensorFlow model. Okay. So this is the transformer, importing the transformer model from PyTorch. And training and testing of the model, and finally the evaluation of the model. So once the model is trained, we are getting, for different epochs, we are getting different performance, and this is the confusion metrics, and finally the classification reports. These are some of the classification reports, report results. Okay, so this is a simple example. I have given a simple example for for speech-based emotion recognition. There are n number of research opportunities in that domain. And another one, what I want to show you in order to do justice with the topic. Okay, let me quickly show you some of the results with our another one project. Okay, where we have done human emotion using facial cues. So Finally, in the last slides, I will show you some of the packages used for all these things, so which will be useful for you. So here also a simple example for face-based emotion recognition. So the 6 cardinal emotions: happiness, sadness, the images in the first, second, and third rows belongs to the FER, JFFPE, and FERG datasets. These datasets are widely employed for the face-based emotion recognition. If those are interested, can note down the name of the dataset. Okay, and the major research gap is the limitation of unimodal systems. Most systems rely only on facial images, lack multimodal fusion. And another one problem is dataset imbalance. And rare emotions are underrepresented. Okay, that we talked in the case of the speech signal also. Generalization issue, good on single data set, poor in real world scenarios. So that is a generalization issue. Real-time feasibility. Uh, the problem is most of the models are computationally heavy. So in order to deploy it in hardware, we need lightweight models, or we need to convert the lightweight models into workable models, which can be embedded into some embedded hardwares. So for example, some FPGA boards, some Jetson Nano type boards, or some STM type boards. So most of the researchers are stagnant in that particular area. As I mentioned earlier, almost most of the works are only in papers, and there are n number of research opportunities. If you can convert a simple paper into a hardware, that itself you can convert it into a good publication. Okay. So because it is the need of the hour as well, because uh, more and more VLSI, research in VLSI and in hardwares, we need more and more research in VLSI and hardware to convert all these papers into a workable model, or to convert all these research into embed all these things into edge devices. We need the hardware knowledge, or how to convert these models to these lightweight models, to how to convert these models that can be workable in an FPGA board or an STM board. There are limited number of papers, because now we are working on that. That is why I am emphasizing on that. I only got limited number of papers which convert the which are there for converting this into real hardware. So that is a electrical and electronics engineers can focus on that area. Okay. And real-time feasibility I was mentioning, explainability also, because many models still functions as black box. So anyway, this is a simple model for again face-based emotion recognition. So this is the architecture. Again, we have incorporated, one is the attention module and the other is the feature extraction module. Okay. So these two parallel paths are combined together. Okay. Are combined together in this particular work. So the model is built on convolution neural network enhanced with the attention mechanism. So instead of processing the whole face equally, the network focuses on key regions, eyes, mouth, and eyebrows, which are crucial for emotion recognition. And we designed the model. The model is shallow. It contains less than 10 layers, but it still achieves state-of-art accuracy, making it lightweight and suitable for, actually we tried to convert this, to embed this into a real-time hardware. Okay. So this is the architecture. So it contains one attention path. Okay. and one feature extraction path. So these two paths. And these are some of the database we have used for comparison: FER 2013 and CK plus and JFE and FERG data sets are some of the data sets which we have employed, and some of the sample images from FER database. And these are some of the sample images from CK plus database, sample images from JAFE database, and sample images from FERG database. Okay, so we have used Adam optimizer and dropout regularization. We have used dropout with L2 regularization, and 300 epochs were done. Data augmentation was done. Okay, flipping, small rotations, distortion. Okay, and oversampling is applied to underrepresented classes to make it balanced. Okay, so these are some of the results. Okay, the detected salient regions for different facial expression using the model. The image in the first and third rows are taken from the FER dataset, and the images in the second and fourth rows belongs to the extended concatenate dataset. So the performance accuracy that we got is like this: FER 70%, FERG 99 with strong generalization, and JAFE 92.8%, competitive with CNN and SVM models. CK plus 98.0% accuracy, and the key advantage is even though this is a number one, it is a lightweight model and fast, interpretable, and real-time FER. So this is the performance measures, and these are the confusion matrices with different data sets. And here the validation accuracy on, I have shown the validation accuracy on FERG data set. The strength is the model learns effectively and achieves high accuracy on FERG, but the limitation is there are fluctuations, shows that the model is overfitted, which shows instability. That means we have to revise the model, highlighting the need for larger or more diverse data set, and we have to work on regularization or dropout, weight decay, and better training strategies such as early stopping or learning rate scheduling. All these things are to be adopted to reduce the overfitting. Okay. So understanding model attention through region masking, that is also we have done. The impact of zeroing out different image parts on the model prediction for a happy face, the top 3 rows, and angry faces, bottom 3. So some part we are making 0 and evaluating the model performance. Okay, and zeroing out face region test the importance of local features in emotion prediction, shows which areas are more critical for classifying emotions, ensures the model focuses on meaningful facial cues and not the background artifacts, and helps improve interpretability and guides design of a robust recognition system. Okay, and the advantage of the proposed model is high accuracy. Anyway, all the models have got its own advantages and disadvantages, but I can focus on limitations so that some people can work on the limitations. So the one limitation is overfitting. Validation accuracy shows fluctuations at higher epochs. Data set dependency. So tested only on these 4 data sets, and sensitive to severe occlusion. Accuracy drops when key regions are masked. So for example, eyes or mouths are masked, the sensitivity or the performance decreases. And emotion complexity, that limited to basic emotions, struggle with subtle or cultural variations. Only it can work with standard emotions. not subtle emotions. Okay. Deployment challenges. Real-time use may face computational limitations. And future work is expand data diversity, include larger real-world data set with variations in pose, lighting, and background. Address overfitting, handle complex emotions, enhance occlusion robustness, optimize for real-world deployment. Okay. And I can show you another one example. Okay. Which is one of the use case of the problem that we have, of the problem that we are discussing. Okay. Emotion-based happiness scoring using EEG and face. Okay. So this is some of our BTech students. They are working with the socially relevant project. The socially relevant project starts at S3 and it will be ending at S6, sixth semester. So between these semesters, they can work with a socially relevant project, and the final evaluation is on S6. And now the students are in S5. So these students, they are working happy to find out the happiness index in our institution. But for the pilot study, they are working, they are developing the code based on some of the data sets. And they are planning to work find out the happiness index using EEG and face analysis. Okay. So happiness index in the sense how far the faculty or how far the students in the campus are happy. Okay, so similar type of works are going on. So the application is in gaming, therapy and counseling, mental wellness and emotion tracking, emotion aware AI systems in education system. We would like to find, especially in the present age of hectic clerical works under NBA, NAC accreditations and all, finding happiness index of faculty and students is also a relevant thing. Okay. So here they are combining the two. Okay, EEG and face they are combining. This is one of the use case where multimodal fusion, and finally based on the fused score, they are calculating a happiness index score. Okay, they are using for EEG, they are using KMEA dataset. Okay. For the model development, they are using that, and here different types of features are taken for EEG. Say for example, the time domain features like mean variance, skewness, kurtosis, zero crossing rate, for frequency domain, power spectral density, spectral entropy, different types of delta, theta, alpha, beta, gamma frequency bands, and time frequency features and all. So they are using Python and model development. They are planning to work with, after developing the model, they have to deploy this on STM32. So finally, they are converting the prediction score into happiness score. Okay, based on the happiness score, they will be finding the happiness index and the same thing. And finally, they need to embed this in a hardware for deploy it in STM model. Okay, for that they need to quantize, pruning and quantization should be done. Okay, so convert C code using STM32 by AI, and so these are some of the use cases what we are talking now. And now coming to the fusion, there are multimodal fusion. There are different types of fusion. Fusion can be done at early stage, which is called feature level fusion, and late fusion, which is called the decision level fusion. Finally, hybrid fusion, which can be a mix of feature level fusion and decision level fusion, which integrates both to balance the intermodal interaction and robustness. And the challenges in human emotion recognition, most of the things that we have discussed, data quality variability, inter-subject variability, multimodal synchronization, feature extraction and fusion, real-time processing, limited and imbalanced data set, ethical consideration, privacy and consent, bias and fairness, emotional manipulation, autonomy and human dignity, transparency and accountability. And future trends is multimodal fusion paradigm, explainable AI, real-time edge deployment of the systems, advanced physiological sensing. So instead of using standard basic signals, we can use some of the modern features such as functional near-infrared spectroscopy, FNIRS, and the galvanic skin response, which is called, we were talking about galvanic skin response based on the emotions, GSR, okay? And ethical and responsible AI. And now coming to the tools, okay? For speech and emotion recognition pipeline often uses Librosa or PyOpenSmile to extract MFCC, prosody, energy, pitch features, etc. And scikit-learn, PyTorch, and TensorFlow for training the classifiers, SVM, CNN, LSTM, and transformers, and finally Matplotlib or Seaborn for the visualization purpose. And coming to the face recognition, face detection and pre-processing, OpenCV, MediaPipe, DLib for detecting faces and aligning the faces. For feature extraction, DLib, MediaPipe can be used. For classification, again, scikit-learn. For shallow models, we can use scikit-learn and PyTorch or TensorFlow for CNN and LSTM. Also for transformer models, we can use this PyTorch. For visualization, again, Matplotlib and Seaborn or OpenCV for real-time webcam-based face emotion recognition applications. And mainly popular research combinations are MediaPipe plus PyTorch and OpenCV plus TensorFlow or Keras for CNN model for training. And the conclusion is the future of human recognition will be holistic, integrating multimodal signals, transparent, providing explainable, it should be transparent, explainable, responsive, operating in real time on edge devices, and context aware, adapting to environment tasks and user history. And we should also consider the ethical considerations, prioritizing privacy, fairness, and human dignity. And the ultimate goal is not just to detect emotions, but to enhance human well-being, safety, and productivity in a respectful and a collaborative way. So I hope with this, I will stop. And if there is any queries, I'll be happy to.
Hi, sir. Sir, this is Rafiq, and one question from Nina through chat box. So how do we calculate the parameter count of this model to state it is a lightweight model?
How do we calculate the parameters? To calculate it is a lightweight model. So there is not a so most of the models it will be having billions of millions. So for example, transformer model, or if we are using some transfer learning models, it will be contain billions or millions of parameters. Okay, so the one thing I can what I can tell is, if you are transferring your if the number of parameters, based on the number of parameters, we can say, so the number of parameters depend upon the number of layers for the deep learning model. So if the number of parameters is less, and if you are converting it in, if the size of that model, if the size of the model is small, so for example, if most of the models are using for if say for example, while deploying in hardware, most of the STM32 devices, the RAM, the memory size is very small. So 2 MB or 4 MB, like that. The flash memory size is very small. So it is very difficult to deploy high models into these particular hardware. So if the number of parameters and if the number of layers and the number of parameters are less, it can be considered as a lightweight model. I can cite an example. An example for a lightweight model is MobileNet V3. MobileNet. So most of the AI models which can work on the mobile phone, which is dedicated for mobile phone applications, can be are lightweight models. I hope the concept that I have mentioned is clear.
Yes, sir.
The
Yes,
number
sir.
of parameters, and the size in the memory, it should be very small.
She asked one more question, like parameters means, sir, something like, can you expand a little bit more about what are the parameters or something like that? She asked.
Parameters means, in coming to deep learning, there are two types of parameters. One is normal parameters and the other is hyperparameters. Normal parameters, if you know about the neural networks, you might be heard about the weights. Okay. The weights, actually the weights are the parameters. Okay. We are changing the weights. So for example, I can say you an equation, y is equal to mx plus c. So there y is a variable and x is a variable. Y is equal to mx plus c. Here, where we can change the slope m and y intercept is c. So that is an equation for a straight line. So by varying m and c, you can have different equations. By varying the slope and y-intercept, you can have n number of equations. Similarly, coming to neural network, you can have a similar equation. Okay. So there you are changing the weight parameters similar to m and c. Okay. There you are having, you are changing the weights. So actually what we are giving is, we are feeding some input, we are getting some output. We want some desired output and the model will be predicting some output. So we want to reduce the predicted output and the actual output. Okay, so there will be an error. So in order to reduce the error, we need to adjust the weights. We need to adjust the weights of the neural network. That is what is the concept of backpropagation. And through backpropagation, what we are adjusting the weight parameters. So weights can be considered as a neural network parameter. Whereas I was mentioning about hyperparameters. So if there are n number of layers and there are thousands of neurons connected, artificial neurons connected, so there will be millions of weights. So you are changing the millions of weights in order to get the desired output. So all these weight parameters can be considered as parameter. Also, there are some hyperparameters. Hyperparameters are user-defined parameters. Say, for example, learning rate of a model. So the learning rate of a model, I am fixing that the learning rate should be 0.7. So user-defined parameters are called hyperparameters. So both parameters and hyperparameters constitute, in general, the parameters in a machine learning or in a deep learning model.
I think you explained all things related to that AI and machine learning, that weights and all the other things. So one more question: how can we find the memory usage during training time when we apply it in edge device?
How can
we find the memory usage during training time when we apply it in edge device?
That actually I mentioned earlier, based on the size of the model, based on the how many RAM. You suppose you have a trained model. When you are saving your model onto the particular device, how much memory it will consume, it depends. So that only by doing that we can understood.
Yeah, I what I understood is, like sir is told, like because of the requirement for this hardware implementation is more, so we are we are reducing the parameter number or lightweight models we are preferring because of the hardware.
But the one thing we can do before employing into hardware, there are some processes called quantization and pruning. Pruning and quantization are the two techniques to reduce the size of the weights. So pruning and quantization, I can say for example, if you are using 50 significant digits after a point. So quantization means by using rounding or truncation, you can reduce the number of significant figures after the point. So by pruning and quantization are some of the techniques used. So there are lot many softwares available for doing this. While converting it, while converting your C programming. Actually, we are doing this in Python, while most of the people are doing it in Python or MATLAB. But while deploying it into embedded devices, you have to convert it into C language. So there are softwares which by default convert the Python programming to C programming of which can be used for the edge devices. Okay, so for example, the Jetson Nano or STM32 like machines. So before, while applying that, they used the quantization techniques and pruning techniques to reduce the size of the coefficients. So for that rounding, like truncations, so you are optimizing your model. So the size of the optimized model, if it fits to the flash memory of the edge device, you can very well use. Otherwise, you cannot use that.
Yeah, that means the optimization is the trump card for these kind of.
Yeah.
Okay, I think everything is clear with these answers, and Saifa, please.
Thank you, sir. The session was really exciting and delightful. We extend our heartfelt we extend our heartfelt gratitude to you, sir, for delivering such an enlightening session on human emotion detection using physiological signals. Your thoughtful perspectives and lucid explanations have provided us with a better grasp of this exciting field of research. We truly appreciate the time, effort, and knowledge you shared with us today, which has greatly enriched our learning experience. Thank you, sir. Thank you once again.
Okay. Thank you, Saifa. Thank you, Rafiq sir. Shall I leave?
Yes, sir. Thank you so much.
Okay.
Have a
Okay.
nice
Thank
day.
you. Okay.
Thank you all participants, and tomorrow we will start around 6 p.m. And there are two sessions tomorrow. Both are very interesting. Like they are explaining about different parts of the body tissues and their problems, like prostates and quantitative evaluations. So all of you, please join tomorrow at 6 p.m. And thank you all for the participation. Good night, all. See you tomorrow.
Thank you, sir. Good night.